Good morning, everyone. Welcome to the Global Quantum and AI Program 2024. We just opened the waiting room for the second day of the program. Today, we will have a fireside chat and Q&A with Olivia Lanes, followed by the second lecture in Q Bronze, Introduction to Quantum Computing and Quantum Programming with Gibran. We will wait a few minutes until everyone is entering. And I see still the count going up and down. The team is quickly clicking so everyone can get in. It was very exciting to see everyone at the launch yesterday. Great numbers, great enthusiasm on the Discord. We are really happy to have this program with all of you, really from all over the world. We saw so many countries on the Discord, and we look forward to learning more about you in the upcoming days and weeks. Some people already started sharing pictures of their world in the Share Your World channel on Discord. Others are helping each other with the starting quizzes and Q Bronze. And we see an amazing community, amazing support. And this is only the start. We will have 10 weeks to come, and then fellowships, continued learning, continued projects. So we're extremely excited about that. I see some messages saying good morning. Yes, good morning to you all as well. And good afternoon, good evening, night. We have many time zones represented. The waiting room is getting emptier, so let's get started. I am sharing my screen here with an overview of the upcoming weeks. Just to review briefly for the ones who weren't there yesterday, we kicked off the program this week and we'll have an exciting week with, on the one hand, an intro to quantum computing and programming with QWorld, complemented by a Q&A today with Olivia Lanes, a keynote on Friday with Will Oliver from MIT, and games tomorrow, which will help you learn more about quantum. Then the second week, we will focus on quantum annealing in collaboration with D-Wave, with QWorld, and also on quantum hardware in collaboration with NIST. Then we will enter a mixed program of advanced quantum algorithms with classic and guest speakers, artificial intelligence, so not a quantum topic, but very important in this current age, and quantum machine learning. And throughout those weeks, we will also have many virtual lab tours at Google Quantum AI, at Atom Computing, Oxford Quantum Circuits, MIT, Oak Ridge National Lab, to see where it is actually happening, the quantum computing progress. After that, we will start applied projects in quantum and AI with the Naval Nuclear Lab, with Fraunhofer, with Classic, and the people performing best in that, whether it is technical or on the creative side, can win prizes and fellowships. Today, fireside chat and Q&A with Olivia Lanes and the second lecture in Q Bronze. I don't want to take much more time away from that, so let's just get started. Good morning, Olivia. Thank you so much for joining us here today. You joined our program also last year. It was a spontaneous appearance during a hardware panel, and the whole Discord was extremely happy seeing you. So we thought, let's not just give you a few minutes, but 40 minutes here to have a great conversation. And please, everyone, post your questions on Discord. So I can ask Olivia your questions, which is most important. Olivia, you did your PhD in the quantum field at Pittsburgh on superconducting circuits, then joined IBM, and not only in one job, but on the one hand as the North American lead for Qiskit and education, and also as an experimental researcher. Can you share more about your path? Was it always clear that you would be in quantum? How did you get this combined role at IBM? We are all really curious.
Yeah, sure. Thanks for asking. So I guess starting in high school, I knew I was going to major in physics. And you can ask maybe how I knew that, but I think that might be a slightly different question, but since I knew I was going to major in physics, I went off to college and I sort of had in the back of my head that I wanted to study astronomy and astrophysics. And while I was there, I poked around in a few other subjects within physics as well. I did an internship in biophysics, I did some optics work, and then I did do an internship eventually in astrophysics as well. And it turned out I really didn't like it. And I sort of had not a midlife crisis because I was like 19 at the time, but a somewhat crisis. And basically, what I had been studying for and preparing for up until that point, I learned that I didn't want to do anymore. So I had to go find something else. I knew I still loved physics, but I didn't know what I wanted to do with a degree in physics. So, sort of at the last minute, just kind of by accident, I came across this subject called quantum computing. And I thought, why don't I just apply to graduate school to study that? Because that sounds pretty interesting. It was just luck. I didn't really know that much about it. It just sounded really, really cool to me. So, sort of just by process of elimination, I set out some applications to graduate schools that had really good quantum computing programs. And, thank goodness I got accepted to a few of those. Ended up going to Pitt, where I was my advisor's very first student ever. Built a lab from scratch, from basically an empty room, built a lot of qubits, built a lot of amplifiers. And then after that, IBM, I want to say I was lucky enough and IBM was smart enough to hire me. And I ended up in a really, really good spot here. So yeah, now I have a team that's focused on working on education and creating content and enablement material for people of all sorts of age groups and different backgrounds. And in my copious free time, they still let me in the lab. So I can still do measurements and work on the hardware as well.
Amazing. And I can imagine that also helps then in the work on education, know the most recent developments and progress.
Yeah, I think so. I think, you never want to lose your technical lens too far. And as much as I'm very passionate about education and talking to students and teaching, I think it helps me be a better teacher that I still keep one foot in the lab as much as I can.
I see a comment from Astro Yara on Discord saying, "I remember following Olivia Lanes on Twitter, and she discussed how she didn't like what she was studying, and then you found the perfect fit."
Yeah, I mean, nothing against astronomy. Some of my best friends are astronomers, and I still think it's really, really cool. I just didn't want to program the telescope for, all hours of the day. It just wasn't my thing.
Yeah, yeah, and that is fantastic. Finding one's own path, and that doesn't need to be the thing that you thought about maybe some years ago would be the thing. And as you learn, you um, you figure out what can be best for yourself and are
Yeah,
ready to pivot into the right field.
definitely. Yeah. Always have the courage to change your mind.
Great. I will just go to questions from the Discord right away, even though we discussed some with the team, because there are already so many questions. Everyone here, please ask your questions on Discord in the live questions channel. So not on Zoom. We are not looking into the Zoom questions, not on the YouTube live stream, but on the Discord live questions channel. There are questions about entering the quantum field. I will combine two questions. There is Julia from Brazil asking, what are your tips to someone who is in college and wants to learn more about quantum and maybe eventually become an IBM quantum advocate? And then Bhavya from India is asking, is self-studying physics enough to enter the field of quantum computing? Or do you really need to get a degree in physics? Do you maybe need to get a PhD degree?
Yeah. So I would say, in all honesty, self-studying is not enough in quantum computing to be employed. Nobody, at least I don't think, has been hired without some sort of technical degree in the field, or, if you're working in the business side of things, a business degree. So yeah, you can't just self-study and expect to be employed. However, I will say it doesn't have to be in physics. We hire people who have some backgrounds in computer science and maybe it's a bachelor's degree and then they taught themselves a lot more quantum software on the side. Maybe they studied chemistry or engineering. So you do need a bachelor's degree, I would say, to work in the field, but it doesn't have to be in physics. And then going back to your first question, I think, which was what are some tips if you're in college? I think try to figure out, exactly where in the field you want to work, because I get a lot of questions from people all the time. They're like, I want to work in quantum computing. What should I do? But I don't really know how to help you without a little bit more information, because the quantum computing field has gotten so big that, like, I don't know if you mean you want to work in hardware. Do you want to work in theory? Maybe you want to be a project manager. Maybe you want to work with clients. Maybe you want to work on the business development side. Like any field or, subject matter, once it becomes commercialized, there's business people, scientists, engineers, client specialists, all working together in the umbrella of quantum computing. But it's hard to give specific advice unless I know what route you are most interested in.
That also shows how many different people are needed and different
Yeah,
types of skill sets, making it very promising to join the field.
for sure.
There are many questions really about on a range of topics. Um, let's ask the question about different topics in quantum. There was a question. Currently, so many topics are popping up, from quantum machine learning, and then more quantum hardware, advanced quantum algorithms, etc. Are there certain things that you feel are really high potential and that are really useful for people to study?
Well, again, it sort of depends what you mean by useful. Like useful just for, to become a well-read and well-studied person, maybe a little bit of everything. If you mean useful, like I want to go get a career in this, then like, yeah, you might want to specialize a little bit. For me, where I see some of the biggest need in the next 5 to 10 years are computational scientists. So people who have some sort of expertise in a subject that's maybe not physics, but maybe chemistry or material science or finance, anything like that. Someone who comes in with a really technical mind in those subjects, but can figure out how to apply quantum computing to those subjects. So somebody who can learn a little bit of quantum physics, learn a little bit of quantum programming, but has so much background in one of these application areas that they can combine them and hopefully come up with some interesting applications and circuits that we can run in the near term. But then another need that I see is we're always going to need really, really good electrical engineers and mechanical engineers, because not that the physicists are going anywhere. Like there'll always be, I think, room for really smart physicists and really smart computer scientists in this field. But as the field matures, it's going to be maybe less of a hard science and more of an engineering problem. And there are so many interesting and challenging engineering problems that we still have to solve. So we're not quite there yet, but that's something that I'm really interested in seeing explode in the next 5 to 10 years.
Can you share more about the status of quantum hardware, and where is IBM now? What do we expect for the roadmap? What
Yeah.
is fault-tolerant quantum computing and how to get there and when?
Right. Um, so just for a little context, so fault-tolerant quantum computing is quantum computing that aims to build a universal quantum computer. So that's a quantum computer that has error correction implemented in it. So it's a quantum computer that's big enough that we can correct for errors basically when they occur, because the qubits are so prone to noise and errors and stuff like that. And these are the quantum computers that, if they were big enough, would be able to run the algorithms that maybe are most famous, like Grover's algorithm and Shor's algorithm. And nobody's there yet. But IBM does have a roadmap to scale up to that size in the next, I think it's 10 years. We have a roadmap that you can look up, and it's published. Um, where we are right now, our current largest chip, I believe, has 100, or the chips that we're building now, the largest chip that we've built has over 1,000 qubits. But right now, what we're working on is building chips that have about 130 to 150 qubits on them, and figuring out how to make them modular so that we don't have to build one big chip with 1,000 qubits, but we can build a few smaller chips with 100 something qubits and connect them with couplers. So we're studying how to create those couplers now and make them with really high fidelity so that there's no loss of information when information travels from one chip to another. So that's currently the biggest problem that we're working on right now. That's sort of the state of the hardware.
IBM uses superconducting qubits, transmon qubits. What do you see as the advantages of it, but also the challenges?
Yeah, so I love transmon qubits because they're so simple from a mathematical and physics standpoint. They're the easiest thing to build also. If you've ever worked at a fabrication lab like I have, simple is good. Complicated is not So good. It's really, really hard to scale complicated builds, which is why I love superconducting transmods because they're so easy. And the advantages of building transmods are that you have all of the infrastructure already needed to build them, basically, because the same machines that you would use to build semiconductor processors can be used to build superconductor processors. So you don't have to build up this whole multi-billion-dollar fabrication industry, which would be a huge challenge to overcome, I think. You can just use the same machines that already exist. So that's really a huge plus. Saves a lot of money and time and infrastructure that you would have otherwise. Um, the negatives of transmons is that they're very prone to noise and they can decay quickly. But we've seen a really pretty big shift and a lot of progress in that area as well over the past few years. We've built qubits that have over, hundreds of microseconds of coherence time. And, that still sounds relatively short, but we've gone up by a factor of 10,000 in time since I was in, early graduate school. So it's progressing really, really fast. So I'm very optimistic about this technology scaling even further.
That's fantastic. And just a heads up to everyone, some of these famous algorithms that Olivia just mentioned, we will learn very soon. On Friday, we will discuss Grover's algorithm, and it will be discussed more next week. And then, if you want to learn more about these transmon qubits, go to the module 3 on Canvas and go to superconducting quantum computing there. There you will find a very good lecture from Kyle Cerniak from MIT Lincoln Lab, hosted last year, where you can learn all the basics of superconducting quantum computing, including transmon qubits.
Kyle is fantastic, by the way. I know Kyle, and he's just
Yes,
A plus.
great. There was a question about quantum computing combined with how you entered physics, namely from Gautam Kamar from India. How will quantum computing be useful for astrophysics and cosmology? Do you have some insights on that?
Um, I don't think anyone has really been poking around in that space too much yet. So this is an area that we could definitely use some experts like I talked about
Big
in that
opportunity.
specific domain area, because I could definitely see some sort of processing being useful, because anytime you have a ton of data, big data, we look for ways to optimize sorting the data and try to pick out specific signatures or clusters out of what look like just a bunch of random signals. And quantum computers are pretty good at that. So, I could definitely see this being applied to like a dark matter search, or I don't even know. Like, there are some quantum principles that go into supermassive black holes. I'm not an expert in that, but maybe we'll learn something by building the quantum computers that will apply to general astrophysics as well.
Exactly. What do you see as other application areas besides astrophysics that could be interesting in the more near term?
Yeah, so I think in the near term, what you want to think about are things that are chemical in nature. So that might include battery development or green energy or material science, trying to build a stronger, better material for some sort of specific application. Any of that kind of thing is what we're looking at in the near term, because what quantum computers are really, really good at just intrinsically, and you don't necessarily need thousands of qubits to do it, is to simulate an atomic lattice and to simulate interactions that happen on the molecular scale. And it turns out classical computers, even supercomputers, are really, really, really bad at that. And I think I read that like 40% of all time that's booked on supercomputers are built to try to, or a book to try to simulate chemical interactions, which is like why batteries haven't gotten better in the past 2 decades. Basically, it's just sort of impossible. It's too much guessing and checking. Um, and if we could try to develop, models to simulate these interactions before we had to go to the guess and check method, hopefully this would improve a lot faster.
Great. Then to a question from Noga from Israel. Can you share more about error correction? How does it work? What is IBM's current state for error correction? And then, do you believe superconducting qubits will be the end game of quantum computer hardware? Oh, Noga is getting serious.
All right. Yeah. So error correction, basically, the idea is that you have a qubit in the middle of your processor surrounded by a ring of other qubits. And those qubits are used sort of as test qubits, and they can tell when your center qubit that's actually processing an algorithm has an error occur. And it can detect it and basically correct for it in real time by seeing if it's the same answer that it was supposed to have calculated compared to all of the other qubits on the outer ring. So that's the basic idea of error correction. IBM published a really interesting paper a few months ago that showed that actually the amount of qubits that you need in the surrounding outer ring is a lot fewer than we previously had thought, which is a really big deal because previously, if you think you need, 10 qubits to your one computational qubit, that scales pretty badly because then you actually need 10 times the amount of qubits as you might think. And it turns out we figured out that we actually need quite a fewer number than we thought. A large percentage was able to be, chopped off the top. So that makes it scale a lot easier. So that's what we're doing right now. And do I think that superconducting transmon qubits are endgame? Yeah, I think I do. I don't necessarily know if I would bet my money on superconducting qubits becoming the only hardware that anybody uses. I could see multiple modularities sort of winning in the end, or maybe being suitable for different types of applications. But I think that superconducting qubits are definitely going to be one of them.
Great. Then a very good question from Kush. Kush says, considering qubit interactions can also introduce errors in quantum chips, how does IBM address this challenge in their superconducting qubit architecture?
Okay, I have to be careful how I answer this because I don't want to give away any company secrets.
Yes.
But basically, there are interactions that you can turn on or off depending on what specific frequency you're sending your measurement pulse with. And if you send it at a frequency that some of the qubits basically don't interact at, then it's basically like they don't see that signal at all and they don't see that interaction. So if you keep the right frequency and you stay in like the right bandwidth, and you keep it far away from like the qubit interacting frequencies, then you don't have to worry about it. So we just have to make sure that when we calibrate our measurement tones, we're in the right bandwidth.
Thank you. Then there is a question about the current status of hardware translated to applications. Sunil Karki asks, can we make simulations of bigger molecules with the current state of the hardware?
So not yet. We're not at the point where we can simulate bigger molecules than we could with a classical computer. But we're getting to the point where there could be some interesting science to be found at the scale that we're doing now, because it's not just about making bigger molecules, it's about looking for more accurate results and more accurate interactions. And we're right at that point now where we're sort of able to compete with some classical computing techniques, maybe not all of them. Turns out classical computer scientists are very smart and they've been doing this a really long time. So they have a bunch of tricks and tips they can play. And we haven't quite beaten all of them yet. But we're at the point where you can use quantum computers as another tool to verify your model or to verify a solution. Because when you're simulating something, before you go and you actually like test it and make that environment in the lab, you don't know what the right answer is. So we might use a classical method that might say like, oh, the ground state of this molecule should be 6. And we might have a quantum computer that says, I don't know, actually, I calculated that it's 7. And we might need another supercomputer that says, actually, it's 5.5. So when we have another tool that we're able to use to sort of verify that we're on the right path and that all of our answers are sort of coalescing into like the same order of magnitude, we really have something here.
Fantastic. And everyone, thank you all for the great questions. There are really many questions coming in. Feel free to upvote other people's questions so I can see which questions really need to be asked because all of them are really good. Thank you. I see also some really advanced or specific questions that you are all invited to really dive into yourself, because quantum is a developing, evolving field right now. And some of the applications have hardly been explored, especially as we are developing the hardware to get to that stage where there is an advantage. I saw a question about, let me scroll back. Yes, an interesting hardware question from Sanjot. Sanjot asks, how would room temperature superconductors affect the development of superconducting quantum computers? Do you have insights on that?
Yeah, actually, it wouldn't. I know a lot of people are really disappointed by that answer, but we don't care about room temperature supercomputers for what we're trying to do. Our technology is cold for a reason, and it's not just because we want to keep the supercomputer cold or the superconductor cold. It's also because we need to get rid of all thermal noise in the environment. So it wouldn't actually help us, unfortunately.
Thank you for these clarifying insights. um, I will scroll. Yes, a good general question that is useful to know for all the upcoming weeks. People use a lot of terms like quantum advantage, quantum supremacy, quantum utility. What is the difference between these? Is what
Yeah.
Nandan asks.
That's a really good question. So, quantum advantage is like the gold standard. Quantum advantage is basically like when you can do something on a quantum computer better in some way, either it's faster or it's more accurate than any classical computer could do. And we're not there yet. That hasn't happened. Quantum supremacy is sort of ill defined. And it's this idea that, like, any process can be done on a quantum computer faster than a classical computer. So that was shown to be possible for random number generation. So, like, yes, quantum computers can generate random numbers more accurately or faster than a classical computer, but like there wasn't anything you could do with that. Like, it was an interesting experiment, but it was totally not applicable to anything in the real world. And then quantum utility is sort of what I was talking about earlier, where quantum computing is an option for verification to compete with brute force methods. And it's sort of just, we're at this point right now where we're like, oh, it's useful for scientific discovery, but maybe it hasn't become a product yet, like it would for quantum advantage.
Thank you very much. That is very clear. Then a question from Yazid from Palestine, asking, can you compare the field of quantum and the field of artificial intelligence? And Yazid asks, how do the current capabilities and limitation of quantum computing compare to those of artificial intelligence? And how do you see the trajectories in technological advancement?
Yeah, it's a really big question. So I guess first of all, the thing to know is that AI and quantum computing, I know a lot of people think they're dueling with one another right now, but they're really totally different technologies because we've been working our way up to AI and large language models for like the past 40 years. It's just like the next step in classical parallelization of computing. It doesn't really like change the game necessarily. It's using the same basic laws that we've been familiar with since computing became a thing. Quantum computing, on the other hand, opens a whole new avenue and a whole new window into a different type of computing because it simulates with different actual physical laws. So it's not like, oh, well, now that we have AI, we don't need quantum computing or vice versa. They do totally different things. And I think that that's one thing that I want to emphasize to you all. Now, I know AI is really, really hot right now. Like everybody knows, NVIDIA is taking over the world, GPUs to simulate AI and large language models. Like it's great. Um, but it's not quantum computing and it won't be quantum computing and it won't ever be able to do the things that the promise of quantum computing will be able to do. However, we do see ways that they could play with one another and help boost one another. So, for instance, we have a new technology right now that's coming out called the AI Qiskit transpiler, which basically uses AI features to more accurately predict and suggest a circuit and transpile it and optimize it for you for a given processor for a specific purpose. And we found that not all the time, but often it can suggest a better circuit that's more optimized than the non AI transpiler would. So, in that way, AI is helping quantum computing. And in the future, we hope to see quantum computing help AI. There are some things that we've been exploring in the quantum machine learning realm where you can basically add a whole nother dimension to your exploration space, which gives you more ability to create cuts and planar distinctions when you're doing categorization or grouping. And so maybe that could help with large language models in the future. I don't know. That's a little bit further out. Nobody's doing that at any big scale yet, but there's many interesting possibilities. So I think the important thing to note is that AI sort of had, a path, a trajectory that went up and down for a while too. Like AI had a winter where basically there was a whole lot of people that were like, it's never going to work. We're never going to have AI. Let's just stop funding it for 10 years. And it turns out that was a mistake, right? Because if we had kept funding it, we could have had all of the technologies that we're seeing now, like with ChatGPT, a lot sooner. And you could argue from an ethical standpoint, maybe we weren't ready for them, but again, another discussion. But I think the important thing to note is that progress is not linear, right? You're going to see some ups and downs, and you're going to see some people who are like, oh, it's working. Oh, it's never going to work. Oh, it's going to work tomorrow. No, it's never going to work. And like, there's going to be a lot of noise in the field before any trajectory can really be seen.
Yeah. And there are also some models for these hype cycles. If people are interested, also look up the Gartner hype cycle, how that went for AI, where are we currently for quantum, and of course there are a lot of nuances to these models. But since there was a lot of funding for quantum the recent years, I personally definitely think that a lot of progress was enabled to accelerate us on this hype cycle. Um, there are a couple of questions about the IBM Qiskit program and becoming an IBM Qiskit advocate. Could you share a little bit more about that?
Yeah, so the IBM Qiskit advocates are basically people who have some experience programming in Qiskit and have shown to be a leader in their community or at their university or wherever they are right now. And they want to help basically get people excited and interested in programming, quantum computing, and using Qiskit. So you can apply once a year. We do an application where people can basically take a quiz and then fill out basically just a sheet that says what they have been doing, what they've been working on, and why IBM should recognize them as an advocate. I did it a few years ago. I know the process is a little bit different now, but it's pretty straightforward. And basically, if you're excited about this technology and you have some experience programming, I definitely encourage you to apply. I think it offers you a lot of benefits, and it can be a really great way to get connected with people who work at IBM or other people working in quantum computing, and you might not necessarily have access to them otherwise.
Wonderful. Then there are a lot of questions about specific applications, more questions about how to really sculpt their own career path. There was one interesting question. The question is, how to be Olivia Lanes?
You don't want to be Olivia Lanes. I want to put this out there because people always say, like, how can I do what you do? And like, how can I follow your path? And like, this is a bad idea. Don't do what I did. I came here by accident. It was a mistake. It was not on purpose. I didn't have a plan. And so I don't know how you can replicate that or why you would even want to. Follow your own path and figure out your own things that you're good at. I just found this path and found this job because I tried this thing and I was like, oh, nope, don't like it. Let me try this thing. Oh, no, I'm not good at that. Let me try this. Nope, still don't like it. And I just basically was a pinball bouncing through life, just making, the best educated decisions that I can based on what I like and what I'm good at. And I super encourage you not to follow anybody's path, but to just do that same thing for you. And you might end up somewhere that you didn't even think of.
Perfect. I receive messages of people saying relatable or so we should make mistakes. Yes, find your
Yes.
own path, explore.
Oh my God, yeah. Do you know how many things I tried that I was like, that sucked. I don't want to do that again. I think that's human nature. And if you're not finding those things, you're not exploring enough.
Exactly. Fantastic. I will browse through all the questions to get to some final questions. Are there some things that we skipped, Olivia, but that you would really like to be asked? Or something you would really like to share?
Oh, geez. I don't think so. I know we hit a little bit of everything. I guess one thing that I'll caution people on, especially younger students, because it can sort of be hard to tell, like when announcements come out in the field, like how big a deal is this, or like how exciting is this actually? Is it just a marketing message, or is it actually like a new scientific step? I would say just find a few people in the field that you trust, that are, you know, that have good integrity scientifically, and follow them. Follow them on LinkedIn or Twitter or whatever other platform you prefer, and listen to what they're saying and listen to what the experts are agreeing upon. Um, you'll see, all sorts of people pop up and be like, I mean, I see this even in the past like 2 days. Someone was like, I ran Shor's algorithm. I've achieved quantum advantage. It's like, no, they haven't. Like they're, for lack of a better word, lying. So be careful of that. And even if you're not at the level yet where you can use your own technical expertise to really, sort through the weeds, find a few people that you trust, reach out to them if you're curious, or just follow them and see what they're discussing and what they believe.
Great. And there are indeed multiple questions about that. For example, Rishwan asks, can quantum computers crack crypto encryption, or is this just a myth? What are your thoughts on that now and for the future?
So there are some crypto algorithms that are vulnerable to quantum computing. Not all of them, but some of them are. However, that's like so many years out that I'm not worried about it.
Exactly. And great. There are many questions, which means that people, you are in the right place. We will have 10 weeks to go to learn about all of these. There are also some questions about comparing superconducting with photonic quantum computers, many about specific applications, whether it's in bioinformatics or for the brain or for agriculture. Um, and maybe let's do one last question about really the skill set needed. Natasha from the UK asks, what kind of skill sets are required to jump into the quantum industry? Could you give some last career advice, share about the skill sets and people's paths?
Yeah, so I like I mentioned before, it really matters where in quantum computing you want to work to develop your skill set. But in general, I think the best things that you can do for your career are to learn how to have some technical chops and to be able to read through scientific papers or at least press releases yourself and understand like what they're saying, and even more importantly what they're not saying, what they're leaving out, and be able to explain it to other people. Like you should practice explaining what you understand technically towards people who are not technical or might have a different background than you. I think a lot of my success came because I was just really good at teaching, basically. And I was good at basically being a translator of really dense, boring scientific literature and translating it into things that people understand and the layperson might actually care about. And I think scientists have been neglecting that skill and haven't really been practicing it for a long time. Not everybody, but a lot of people. And on the other side of things, I think there's a lot of non technical people who are afraid of sinking their teeth into the technical aspects of it because they think they might not be capable of it. And that's false too. So I really think there should be a better merger of what we might say are soft skills or business skills and technical skills. And you want to be in the middle. You don't want to be too far on either side. You really want to have a good balance of both. I think that's my best career advice.
Like, then last question from Negar from Turkey. When will the next Kiskit summer school take place?
It is taking place in July. Yes, I think it starts July 15th, and signups are going to be very soon. So just keep checking LinkedIn and Twitter. We're going to make the announcement in like a week or two.
Fantastic. Olivia, thank you so much. This was a great conversation and great Q&A. Thanks to everyone for sharing all these great questions. And Olivia, thank you for being ready to answer all of these. Let's keep in touch. And you are on Discord now as well. So we look forward to keep collaborating and then have a great Kiskit Summer School
Thanks.
and all the other endeavors.
Yeah, thank you so much. Thanks for having me, guys.
Thank you very much. Everyone, thank you for all the great questions. We will have a little break now, and then we will enter the second part of this session, namely the Q Bronze second lecture with Gibran. But I would like to take the opportunity now to also introduce one more team member, Jasmine, who has been answering lots and lots of your questions on Discord. We just added your spotlight, Jasmine. Would you like to introduce yourself to everyone?
Oh, hello. So I am Jasmine. I did the Womanium quantum program last summer and really enjoyed it. And I was very excited to come on as a volunteer and help them do more of that in the future. So here I am again, messaging all of you like mad. You are wonderful souls, so we will get all of this resolved. But yes, my background as far as quantum, I got into it in high school. Towards the later part, I knew I loved computer science at that point, and I loved physics and AP physics. And then I heard about quantum computing from a sci-fi teen novel, and I thought it was like, oh, this is a plot device to keep the book moving, right? Like that's kind of too cool to be real. So I Googled it. It's like, no, it is real theoretically. And I thought that was amazing. So I looked into it more and I loved it. And as I went through college after that, I took any chance I could to study and learn about it more through books and courses or classes at my college. And now I'm a software engineer by trade and a quantum enthusiast hobbyist by passion. So that's what I do.
Amazing. And Mohammed Ali from Iran says Jasmine is a perfect team member. I agree. IBM from the US says, me too, software developer and quantum enthusiast. Great. Feel free, everyone, to take a brief break now. I will bring up the break slide to make it clear to everyone. Here we go. Should be sharing screen right now. And then in a few minutes, we will start the next part with Gibran.